Here we're asked to determine if Picard's theorem does or does not guarantee existence of a solution to the given initial value problem. If existence is guaranteed, determine whether that solution must be unique. Now, before we get into this problem, let's review Picard's theorem for existence and uniqueness. So, Picard's theorem is stated as this. If we have our derivative, y prime, which is a function of x and y, if we can show that it is continuous as a function of two variables, and the partial derivative of our function f of x comma y, which is our y prime, if we take a partial derivative of that with respect to y, if that also exists and is continuous near the point of interest, then the solution to the differential equation at this initial condition must exist and is unique. Now, here's a key point to think about here as well. If we can show that both this is continuous near to our initial value and this is continuous near our initial value, then we know our solution exists and is unique. However, if we can show that this is continuous and this is not, we still get that we have a solution, but we can no longer be sure that it is unique. So if we can only get the first criteria, we still have a solution, but not necessarily a unique one. So to answer this question, we really have to figure out the answers to two questions. First, is our given y prime dy dx continuous near our initial value of 0, 0? We know that the cube root function is continuous everywhere, so it's definitely continuous near our point. So the answer to this first one is yes. Next, we need to take the partial derivative of this with respect to y, so we find that df dy is 1/3 y to the negative 2/3, which we can rewrite as 1/3 times the cube root of y squared. And now we need to consider, is this function continuous and does it exist near the point? So first of all, what do we mean by near? We mean at the point and also some distance away from it, though it could be a very small distance there in all directions. Looking at this problem, think about what happens if we look specifically at the point. Since it's 0, 0, the y value is 0. What happens to this equation if we were to plug in 0? Well, 0 squared is 0. The cube root of 0 is 0. 3 times 0 is 0. And we would essentially be looking at something that's like 1/0, which we know is undefined and does not exist there. So is it continuous near 0, 0? Since it's undefined at the point 0, 0, it cannot be continuous at that point, because one of the conditions of continuous, although there's a few others, is that you have to have the point defined. So the second condition fails. And what that means for us is that we do have the existence of a solution because we met our first criteria. The differential equation is continuous near 0, 0. But Picard's theorem does not guarantee a unique solution because our second condition failed. Here we're asked if it's possible to solve y prime equal to xy for the initial value 0, 0. And then we're asked, is the solution unique? And we need to justify our work. So what comes to mind again is applying Picard's theorem. We need to determine first, is the derivative, the differential equation we were given, is it continuous near the point in question? And if so, then we take the partial derivative with respect to y and see if that's continuous near the point as well. If both of those are true, then we have the existence of a unique solution. So let's consider our first part of this. We have y prime is equal to x times y. So just think about this function. At the point, 0 times 0 is 0, that's no problem. And think if we kind of deviate, if we take negative x values very close to 0, there's still no problem. Negative y values, very close to 0, still no problem, and the same for positive in both the x and y direction. So this problem has no issues near to our point 0, 0, so we would say it is continuous. Another way you could think about this is x is continuous, y is continuous, the product of continuous functions is continuous. Now we need to take our partial derivative, and we need to take the partial derivative with respect to y. So here we're going to treat x as if it's just a constant. So think about the way you would take the derivative of 3y would just be 3. But in this case, our constant is x because we're taking the derivative with respect to y. So df dy is just x times 1 because the derivative of y with respect to y is 1. Multiplying by 1 doesn't change anything, so our partial derivative with respect to y is x. That's definitely continuous near 0, 0. So since both of these conditions are met, we know Picard's theorem guarantees us the existence of a unique solution near to this. Is it possible to solve the equation y prime is equal to x times y, all divided by cosine of x, for the initial condition 0, 1? Justify your response. So here we're not asked to solve, that would be a different type of question. We're just asked, does the solution exist? And at this point, hopefully Picard's theorem comes to mind, and then we know we need to check two things. First of all, is the differential equation we are given, is it continuous and exists for points near to the initial value? Once we've checked that, we know we need to take the partial derivative of that with respect to y and see if it exists and is continuous for points near our initial condition. So let's work through that. Now looking at our equation, y prime equal to xy divided by cosine of x, I'd ask you to take a moment and look at the way this function is structured and ask yourself, what type of x or y values could cause this equation to have problems? As you ponder that, hopefully we focused in on the denominator, because we know functions that involve fractions, the denominator better not go to 0. So in our mind, we're thinking about, okay, when does the denominator go to 0? That's when does cosine go to 0? Well, that's going to be at odd multiples of pi over 2. However, the point that we're looking at is when x is near 0, which is not near pi over 2. So the only points that would cause this function to have trouble are not near our initial condition. So with that reasoning, we're like, okay, everything is fine. If we plug in a 0 here and a 1 here, we would end up getting just the value 0, because we would get 0 times 1 over 1, which is 0. So it is continuous near a point. Now let's look at our next one. Is the partial derivative continuous near the initial value? Here we need to take the partial derivative. We know we're taking the partial derivative with respect to y, so if it helps, I'm going to rewrite our function f, function of x and y, as x over cosine of x times y, just kind of rearranging it slightly. And here this helps me focus on the fact that this should be treated as a constant throughout. And we know the derivative of a constant times the variable that we're taking the derivative with respect to is just the constant term. So our df dy will just be x over cosine of x. Take a moment to consider, should that be continuous and does it exist for values near to 0, 1? Again, in our mind, we know the only issue for this particular looking function is when our denominator is going to equal 0, which would only occur at odd multiples of pi over 2, so definitely near to 0, 1, it does exist and is continuous. Since both conditions are met, we know that we have the existence of a unique solution. Next, we're asked to sketch a slope field for y prime equals y squared. And we can begin doing this by plotting a few points. And then as we do so, we really want to look at how the function behaves so that we can extrapolate based on the function's behavior and kind of know what's happening even if we don't plot every single point. So let's consider what happens if we fix x values and go through some different y values. So for instance, when x is 0, that would have us on the y-axis. What would happen if y was 1? Well, we know that we look at the equation and we see that there's no place to plug in 0, so this differential equation is unaffected by what x value we choose. However, whatever y value point we're looking at, we need to square it to get the value of the slope. So 1 squared is 1. So similarly, if I looked at 0, 2, again, the x value doesn't apply here because this function is only in terms of y, but it tells us that we should square the y value, so we should be looking at a slope of 4 at that point. And here we start to see a pattern. Think about what would happen at 1, 1 and 1, 2. What would be the slope? Just like we said before, the x value for this particular function is irrelevant. You just square the y coordinate. So at 1, 1, we would have the same slope as we had at 0, 1 because the x values don't come into play. We just square the same y value and we get 1. 1, 2, we get 4 as before. And with that, we can start to draw out some patterns. For instance, we know for every point along this height y equals 1, the slope should be 1. For every point when y is equal to 2 at any x value, the slope should be 4. At any point when y is equal to 3, think about what the slope should be there. 3 squared should give us 9. Now what happens when both we have the y equal to 0? So for any x value, the y value on this line is equal to 0, so the slope should be 0 as well. So here I'm picking points at the integer value, so negative 3, 0. I showed that the slope is 0 by drawing a flat line. Similarly, we know here at height y equal to 1, all of these slopes should be 1 from our reasoning. And if I wanted to, I could also draw in the slopes, for instance, at the 0.5 value of x. But I'm just going to keep it at the integer portions. We know at height 2, we should have a slope of 4, so I'm going to show that to have more steepness. Height 3 should be 9. And now let's consider what happens when y values are negative. So as discussed before, we know that this doesn't care about the x value, so no matter what our x value is, when the y value is at height negative 1, that would be negative 1 squared, which would give us 1, negative 2 squared, which would give us 2, negative 2 squared would give us 4, and negative 3 squared, which would give us 9. We can plot that on our slope field. Now, if we plotted more points at a greater density, our slope field would give us a better picture of what's going on here. And we can kind of reason about what will happen too if we just think about what's going to occur with our differential equation. Think about what would happen to the slopes as the y value increases. Since a slope is found from y squared, the larger your y value gets, the larger the slope gets. So as the y values increase, the slopes will eventually be approaching vertical asymptotes, becoming vertical. Same thing as we have our y values decrease, even though their y values are getting farther and farther negative, since we square it, it still becomes a larger and larger positive number. Now, often we'll want to visualize the slope field in a more detailed way. So you could easily go to GeoGebra, just type into the search engine slope fields GeoGebra, and this nice applet will come up. And all we did here is we just typed in our equation. So in this case, the derivative is equal to y squared. And I moved the density over to the farthest that I could to make it more dense. And as we zoom in here, we'll see our slope field, following the same ideas that we found previously in our own sketch. Along the x-axis, the slope field should be 0. And definitely as you square a number between 0 and 1, it should be getting smaller. So we see for values between 0 and 1, and 0 and negative 1, the slopes are getting flatter because the closer you get to 0, the smaller the slopes are becoming as we square it. However, as we move away from 0 in both the positive and negative direction, since we're squaring those, our slopes are getting steeper. Here we're asked to sketch the slope field of y prime equals to y cubed. And then once we've done that, we would need to identify the solution that satisfies the initial condition y of 0 equal to 0. So if we'd find it useful, we can definitely plot points off to the side like we did with the last example. But for practice, let's just work through our slope field by thinking about how the equation acts for different x comma y points. Looking at our equation, we see it's only in terms of y. So we know for each x comma y point, we really only have to know, okay, what's the y value? Whatever it is, we cube it, and that gives us our slope. So for instance, along our x-axis, we know the y value at all of those points is 0. 0 cubed is 0, so that tells us the slopes along that will be 0. So we add that to our slope field. Next, let's consider what happens for y values equal to 1. So in this case, the y value is 1, you cube 1, you get 1. So the slopes along here should all be 1. Next, when y is equal to 2, we know that we cube 2 and we get 8, so the slopes are increasing steeply here. And then when y is equal to 3, cube 3, you get 27. So we'll kind of sketch that and show that the slopes are getting steeper faster than before because our derivative is now y cubed as opposed to y squared. And we can quickly draw this table off to the side just as a legend to show us, because we can see the slopes are increasing, but this tells us exactly what they are at our given points. Now consider what happens as our y values become negative. We know that negative 1 cubed is negative 1, negative 2 cubed is negative 8, and negative 3 cubed is negative 27. Now that's detailed enough for our picture here, but take a moment to consider if I was to show more detail and, for instance, show the slopes when y is equal to 1/2, or when y is equal to negative 0.25, etc., what would be the pattern? How would you describe the slope fields as the y value approaches 0 from both the positive and the negative direction? It would come down to cubing a number between 0 and 1, and when you cube a number between 0 and 1, it gets closer to 0. So the closer we are to 0, the flatter the slopes are going to appear, and we can see that in our more detailed drawing that we got from GeoGebra. So here we see between 0 and 1, the closer we get to 0, the flatter our slopes are appearing for those points. Similar to our sketch, the higher the y values get, the steeper the slopes. The lower the y values get, we get a more negative slope.